think we can start. So our next speaker is Wolfgang Mulzer, professor at Freie Universität of Berlin and PhD student of one of the forefathers of computational geometry, Bernard Chazelle.
Yes.
Welcome, welcome, Wolfgang. He'll talk about asymmetric convex intersection testing.
Yes, thank you. Okay, so this is joint work with Luis Barber, who's now a postdoc with Martin Yagi at EPFL Lausanne. And I will talk about asymmetric convex intersection testing. So that's a problem from computational geometry that has some machine learning or learning motivation. So let's see what the problem is. So we are given a point set P in high dimensions, D dimensions where D is high but constant, so say 100. And we consider these points to be samples. And these samples, they define a sample space. And since we're doing computational geometry, so the sample space, so the space of all the samples or that is spanned by the samples is just the convex hull of the point set. So here we see a two-dimensional example, but of course it could be in high dimensions. And so on the one hand, we have the samples, and on the other hand, we have some set of linear constraints, which we call H. And these linear constraints, they're defined by oriented hyperplanes. And now the question that we have, so these constraints, they define a feasible space, which is basically just the intersection of all the oriented half spaces that we have given by these hyperplanes. And then the question that we have is whether there exists in our sample space a feasible point, a point that is contained in the feasible space. So what we want to know is, does there exist a convex combination of the points from our sample space that satisfies all the constraints that lies in the feasible space? And of course, so if you know something about high dimensional computational geometry, then you recognize that I'm talking about polytopes here. So both the sample space and the feasible space, they're polytopes, and they are given in two different representations. One of them, the sample space, is called a V polytope, which is just a high dimensional polytope that is defined as a convex hull of its vertex set or convex hull of any point set. And the feasible space is just an H polytope. And an H polytope is just a polytope that is given as an intersection of half spaces, or typically a bounded intersection of half spaces. Okay, and so the question that I have is whether, if I have two polytopes, whether there exists a point in the intersection, and I want to solve this quickly algorithmically. And the special twist in the way I present the problem is that the two polytopes where I want to know whether they intersect or not, they are given in two different ways. So one polytope is given as a V polytope, as a convex hull of a point set, and the other polytope is given as an H polytope, as an intersection of half spaces. And this somehow makes the problem more difficult. And before I talk about this variant of the problem, let's talk about the classic or more well-studied version of the problem, where we're given two polytopes and we want to know whether there's a point in their intersection, and the two polytopes are either both given as V polytopes or both given as H polytopes. And if this is the case, then it's quite easy to see that this is just a variant of linear programming problem. So this is just linear programming feasibility, basically. If we're given two H polytopes and we want to know whether there's one point in both of them, then this is just a feasibility problem for linear programming and can be solved quite quickly. So in particular, if the dimension D is small, then there exists quite simple and satisfying algorithms. So for example, if I know that the dimension is constant, then I can find, and I know the two polytopes are given as polytopes in D dimensions with n constraints. So let's say I have two H polytopes in D dimensions with n constraints, then Chan showed that we can solve it deterministically in time d to the O of d times n, which is linear in the number of constraints if D is constant. And there also exist randomized algorithms from the 90s that are even better. So where basically we have some term which is linear in n and polynomial in D, and then some term which is somewhat exponential in D, or sub-exponential, depending on how you call it. Okay, so this is the nice thing. So if both of the polytopes are given in the same description as V polytopes or as H polytopes. It's a problem that is well understood. But now the question is, what happens if the two polytopes are given in different representations and I still want to know whether they intersect or not? And so this is the problem, and that's why we call it asymmetric convex intersection setting, asymmetric because the two convex polytopes are not in the same representation. And so now let me define my notation. So, or let's again say what the problem is. So we're given two things. We're given a point set P of n points, and that defines a polytope by the convex hull of P. And we're given a set H of constraints, and there are m of them, and they define a polytope by taking the intersection of the of the half spaces defined by the constraints. And we want to know whether these two convex hulls, the two polytopes, are disjoint or not. Okay, so this is asymmetric convex intersection testing and testing. And now I want to talk about how we can solve it. And so surprisingly, before our work, it seems that this has not really been studied in the literature, but of course, there's been a lot of work on polytopes and on linear programming and so on. And so we want to first see how much we can use from the existing techniques to solve our problem. And so, of course, I said if the two polytopes are given in the same way, so if both polytopes are given as H polytopes or both polytopes are given as V polytopes, then it's quite easy to solve the problem. And so we can just use a brute force approach. So if we want to know whether the two polytopes intersect, I can just say convert one polytope into the representation of the other polytope. So let's say I just want to represent the convex hull of P as a H polytope. So that just means I need to compute all the facets of this polytope, and this I can use, for example, I can do, for example, using an algorithm of my advisor Bernard-Chazelle. We can just compute the convex hull. Then we find all the facets of this convex hull of P, and then we have two polytopes that are given in the same representation, and then we can check whether they intersect using linear programming. And so, for example, here in the two-dimensional case, I would just compute all the lines that support the segments of the convex hull, and then this gives me some constraints, and now I can use linear programming with the green and with the blue and the red constraints. Okay, and so does that work well? So let's see. Of course, there's a problem with that, or something that might be not satisfactory, because so if we are in high dimensions, then we know if, for example, the points of P lie on the moment curve, then the number of facets of the convex hull of P might be n to the d over 2, up to n to the d over 2. So there might be a number of facets that's exponential in d. And then, so that means I would have to solve a linear programming problem that's in d dimensions. That's fine. But the number of constraints would no longer be linear in the number of points, but it might be exponential in d. So, and of course, I may be lucky, and the number of facets is less, but in the worst case, this may be bad. Okay, so that's one problem. But of course, we could also try to do it the other way. So again, we could just so another approach that we might try is, so we use linear programming directly, but we do not compute the convex polytope of P. But what we do is we write the linear programming with the constraints of H, and we add another constraint that we want to have a point which is in the convex hull of P. So we just use an LP with all the constraints for of H, and we add another constraint saying that we want to have one point which is which lies in the convex hull of P and fulfills all of these constraints. This is also possible, but the problem is that we need to introduce more variables in order to express this convex combination. So basically, we need variables for expressing this convex combination to say that we have a point that is a convex combination of the points in P. And this means effectively we increase the dimension of the linear programming. So it used to be that the dimension of our linear program was D, but if we go this way, then we have to solve a linear programming problem where basically the number of dimensions, so the number of variables and the number of constraints both depends on M or N. And so this is still something that we can solve in polynomial time, but now we cannot, because the dimension is no longer constant, we cannot really rely on these nice linear programming algorithms that we know from computational geometry, like the Chan algorithm or the Clarkson algorithm or the Matuszek-Shadir-Welzel algorithm. But now we have to rely on the heavy-duty linear programming algorithms from combinatorial optimization, like ellipsoid or interior point methods, which are still polynomial, but not as efficient as the ones that we like. And so this is also a bit of a unsatisfactory situation. But there's a third way we can try to approach this problem. So classically, and this is the LP type approach, and LP type, that's also some concept from computational geometry that is supposed to generalize ideas from low dimensional linear programming to problems that are quite similar but not quite the same. So it's an abstract framework for solving problems that look like linear programming in constant dimensions, but are not quite the same. And so let's see how this LP type framework looks like. So in general, so an LP type problem is just given by a set of constraints. And so the constraints is just some finite set. We don't exactly know what they are, so it's abstract. And we have a weight function that gives some real weight to every subset of the constraints. And so, for example, in our case, we could define the set of constraints as follows. We fix the half spaces. We fix the half spaces and their intersection. And the constraints are the points from P. And we define a weight for every subset of constraints by just looking at the convex hull of the subset of constraints, so the subset of points. We just compute the convex hull, and we compute the distance between this convex hull and the intersection of the half spaces. So that just gives some weight like this. And so this this distance can be defined by just one point of the subset, but in general, it doesn't have to be the case. So it might also be that it's defined by a face of the convex hull. So the distance might not be defined by just one point of the subset of the constraints, but by several points. But, and this is the important point, only by points from the constraints that define a face of the convex hull. And so this means that the number of constraints, or the number of points in a subset of constraints that define the weight function, is always bounded. And so this is one of the most important properties that we need to have. So I mean, in order for the LP type framework to apply, we need the LP type framework the LP type problem to satisfy a certain set of axioms. And the most important axiom that that I just tried to illustrate is that there exists a basis. And so this is something that basically carries over from linear programming. So we want that the LP type problem that we want to solve has the property that there is a basis, and that means that there exists some constant d, which is called the combinatorial dimension of the LP type problem, such that for any possible subset of the constraints, there exists a basis in this subset that has at most d elements, such that the weight of the subset C of the constraints is already defined by the basis, right? So in our example, we saw that this is the case for the way I cast this asymmetric convex intersection testing as an LP type problem, because so the weight of a subset of the constraints is just the distance between the convex hull of the constraints and the intersection of the half spaces, and this weight is defined by a facet of this convex hull, and a facet of the convex hull is defined by at most d points. So we know that in this concrete LP type problem that I defined for asymmetric convex intersection testing, it is the case that there always exists a basis. And so this is the most important axiom that we need for the LP type approach to work on an LP type problem, but there are two more. which are somewhat intuitive, and so I'm not going to go into them into more detail. So the other two properties that we need are called monotonicity, which basically means that the weight function, if you take subsets, it can only go up or down depending on whether you want to maximize or minimize. And locality, which basically says that if a basis is violated, whatever this means, we can see that through a local test. And but these two properties are also fulfilled in my concrete casting of the asymmetric convex intersection testing problem as an LP type problem. And now, so this LP type framework was defined by Xavier and Belzel in 1992. And they showed that if you have an LP type problem that satisfies these three axioms, and if there's some algorithmic way of testing for a basis and for a violation of a basis, then you can solve LP type problems efficiently. And so what does it mean? So our goal in solving an LP type problem is we want to find a basis for the whole set of constraints. So we want to find a constant size subset of the constraint C such that the weight of this constant size subset, the basis, is exactly the weight of C, the whole set of constraints. So in our example, what I want to do is I want to find a facet of the convex hull of the points that defines the distance to the intersection of the half spaces. And then either the two intersect and this distance will be 0, or the two do not intersect, and then basically this facet will be a witness showing me that these two convex hulls do not intersect, that these two convex polytopes do not intersect, because I can just check by taking the hyperplane through that facet whether all the points of P are on one side and the intersection of the half spaces is on the other side. Okay, so this is the LP type framework. And let me quickly give you some idea how this algorithm works, because it will also be interesting for us. And so this algorithm, so here we also use some concepts maybe that are interesting for learning theory. So what do we do? So the algorithm is very intuitive. So here we have the points on, and so I mean, the algorithm is abstract. It works in the LP type framework, but I will describe how it works for this concrete setting of asymmetric convex intersection testing. So what do we do? So we just take a random sample of appropriate size of the points. So the green points that you see here, this is a random sample. And I recursively compute a basis for this random sample, right? So, so I recursively look at the convex hull of the green points, and I find the facet of this convex hull that defines the distance to the intersection of the hyperplanes, like this. Okay, and then I have this segment that defines the shortest distance, and I take a perpendicular hyperplane to the segment. And then I see all the points, and then now two things can happen. So it may be that all the points of P lie to the left of this perpendicular hyperplane, and that means I'm done, because now I found the distance between the two polytopes. Or there are some points from P that lie to the right of this hyperplane, and then I'm not done yet, because somehow by taking the sample I omitted some crucial points. And so now I need to look at these points. And how do I look at these points? Well, I just add these points to my sample. And so I make these points green, and I just repeat. I just increase the size of my samples by those points that violated the solution that I have found, and I repeat again. And now the whole theory of epsilon nets and bounded VC dimension tells me that if I choose the sample size appropriately, the number of points that I add here will be small. And right, so we just add and we repeat, and then we find a new hyperplane. And then if we are lucky, maybe this one now will be good. So we find a new distance, and we find a new hyperplane that basically is spanned by this separating segment, and we repeat, and hopefully we're done. And then the question is, how many iterations do we need? I mean, so we just repeat. So first we take a sample, we recurse, we find the violating set, we add the violating set, we again recurse, we find a new violating set, we add the violating set, we repeat. The question is, how often do we have to do this? And the answer is that every time we do this, we will find at least one element of the basis of the whole set of constraints. So at least one of those elements that I add from the violated set, it will be an element of the basis. It will be a point that spans the true facet that separates C from H. And so this is good because I know that this basis has at most d+1 elements. So I know the number of iterations, the number of recursive calls that I need is at most d+1. Oh, sorry, the basis has at most d elements, but the first time there may be no elements of the basis in there, so I have at most d+1 iterations. And then I get a recursion for the running time, so I have to recurse d+1 times on a smaller set on the sample. And then there's this whole time for checking for the violations and so on. And then I can solve this, and I can use the theory of epsilon s to see how large this has to be. And then I get this kind of recursion, which is actually quite good. I mean, so, but the only problem is that at some point I will end up with some subset of constant size. So, I just keep decreasing the number of points in C, the number of constraints. At some point I will have a constant size set of constraints, and then there at the bottom of the recursion, at the base case, I have to do something brute force. And this will be expensive because somehow all the constraints from H are still there. And so I need to find basically the closest pair between a constant size convex hull and the set of constraints, the intersection of the constraints. And this is still expensive, and because the base case can occur a few times. So this still does not give a nice linear time algorithm as I hoped for. And so then what we do together with Luis Barber is, so we try to improve this, and in order to get a simple algorithm that basically works similarly to this classic LP type algorithm, but which is faster and maybe also simple. And so for this, this is what I'm going to explain in the rest of the talk. And for this, I need to also remind you of some quite basic concepts from high dimensional geometry. Because, I mean, so the issue with this LP type algorithm was that we just reduced the number of constraints, so the number of, the number of points from P, but we do not reduce the number of hyperplanes. And what we want to do is we want to simultaneously reduce the number of hyperplanes and the number of points. Or the number of half spaces and the number of points, right? So we somehow want to not, so we want to do it symmetrically. We want to reduce both sides, hyperplanes, half spaces, and points. And so somehow we need to have a way of switching the roles of the half spaces and the points. And for this, of course, we use the polar transformation, which allows us to switch between points and hyperplanes or half spaces. And so let me remind you what this is. The polar transformation is a way how I can transform points to hyperplanes and hyperplanes to points. And so basically what I need to do is, so there's the origin, which is here is shown in purple, and a point P. And now I can make a hyperplane out of this point according to this formula up here, which just says that I take all the points in the d-dimensional space whose dot product with P equals 1. And so this gives a hyperplane, and this is called the polar hyperplane to P. And vice versa, I can also go from hyperplanes to points by using exactly the same formula. So if I have a hyperplane, I can define a point from it by just looking at the point that fulfills this equality. Yes, and so this basically gives us away from switching the rows of hyperplanes and points. And of course, I mean, this is not really canonical. So really the way how we can do this transformation, it depends on where the origin is, of course. Yes, and now let's look at some interesting properties of this polar transformation that will be useful for our setting. And so let me give you some more definitions, some definitions and some properties how this polar transformation plays together with convex hulls. And so here the definition is this definition is of an avoiding point set, and so I call a point set P avoiding if the following happens. I look at the convex hull of this point set, and then the origin is not contained in the convex hull of this point set, and then we call this point set P avoiding. So avoiding means the convex hull of P does not contain the origin. And then there's another definition, or the opposite, or the negation of this. If, on the other hand, the convex hull of P contains the origin, so if the origin lies in the interior of the convex hull of P, then we call the point set embracing. Yes, and similarly, we can have definitions for hyperplanes. I can or half spaces. So I can say I call a set of half spaces embracing if its intersection is bounded. So we need to have the additional constraint or the additional property that the intersection is bounded, and this intersection contains the origin. So a set of half spaces is embracing if the intersection is bounded and it contains the origin. And we can also define an avoiding set of half spaces. And an avoiding set of half spaces means that that a set of none of the half spaces contains the origin. So it's so here for half spaces it's a bit more subtle, the distinction between avoiding and embracing. On the one hand, for embracing, I need that the intersection is bounded, and it is not really the case that not embracing means avoiding, because avoiding means that really that none of the half spaces contains the origin, and not just that is not embracing. Okay, but so these are two definitions. And now the main lemma that we have is that somehow allows us to switch between points and hyperplanes. So suppose we have a set of points in d dimensions, then the point set P is embracing if and only if I look at the dual hyperplanes of these points and orient them towards the origin, that this set of half spaces that I get is embracing. And on the other hand, the point set is avoiding if and only if this appropriately defined set of hyperplanes is also avoiding. Okay, so this means yes, so I mean we have some duality between embracing and avoiding for points and the polar half spaces that we get. This is our lemma for the polar transformation, and this tells us that somehow we can use the polarity transformation in order to make embracing point sets, and so in order to somehow dualize this notion of intersection. So if we have a point set that is embracing and a set of half spaces that's avoiding, so let's assume we have this. So we have a point set that is embracing whose convex hull contains the origin, and a set of half spaces that is avoiding such that no half space contains the origin, or vice versa. Then we can see that basically the two polytopes defined by them intersect in the primal if and only if, in the case that I dualize them and I take a point in the intersection, this point in the intersection will separate the two. So basically we have a way, so maybe this is a bit confusing, but basically what this says is we have a way from going from the primal space to the dual space, and turning the intersection in the primal space between a V polytope and an H polytope to a separation between a V polytope and an H polytope in a dual space. And this is a bit subtle, changing the two directions is a bit subtle because of this, and so because of the way the polarity transformation works, and so therefore we need these somewhat subtle definitions of embracing and avoiding. Okay, so but here's the picture. So here these two H and V polytope intersect, and here's a point in the intersection, and then if we polarize, then we see that this intersection becomes a separation in the hyperplane. Okay, and so now let me quickly describe how we can use this to get some kind of algorithm that switches, that is some kind of analog of the LP duality algorithm, of the LP type algorithm that I showed you before, but that keeps switching between the primal and the dual space and is somehow able to somehow sample both the points from P and the half spaces from H. And so let me quickly describe you how this algorithm works. So the idea is, so first of all, I need to somehow get the setting that one of the two sets that we have is embracing, and one of the two polytopes that we have is embracing, and the other one is avoiding. But that's easy to do. So first, we can use some linear programming, algorithm to find one point in the interior of H, like this one. And now I check whether this point also lies in P, and in the convex hull of P. And this again we can just use using linear programming. But in both cases, the linear programs, they just use all of H and all of P, but not both of them. So this is somehow clean, and we can use the algorithms that we have from computational geometry because we have only one representation of the polytope. And okay, so we test whether this point is in the convex hull of P. If we are lucky and the point is in the convex hull of P, then we're done already because we know now that the two polytopes intersect and we can finish. So let's assume that it is not the case. In this case, we just move the origin to this purple point, and we know that this purple point now lies inside H. So it makes H embracing because we also assume that the intersection of H is bounded. And it also makes P avoiding because we tested and found out that the convex hull of P does not intersect the point in the origin. Okay, so basically we're in the setting that we started for our primal dual polarity approach, that we have one H polytope that is embracing and one P polytope that is avoiding. And that means now basically we can turn the intersection testing to trying to find a separating hyperplane in the polar, and we can go back and forth between the two settings. And now let's see how the algorithm works. I mean, so now we have a general intersection testing routine, and so there we have some hyperplanes or hyperplanes that are embracing, and we have some points that are avoiding. And what we want to do now is either we want to know whether these two polytopes, the H polytope and the V polytope, intersect. And if they do not intersect, we want to find the closest pair. I mean, the point that minimizes the distance between the two polytopes if they're disjoint. And if not, we want to not really find a point in the intersection, but we want to we know if they do intersect, then the polars. The polar polytopes do not intersect, and we want to have a closest pair for this polar non-intersecting polytopes. So this will be a certificate of intersection. And now what the algorithm does is, so here we have the picture. What the algorithm does is it again takes a random sample of the points of appropriate size, and it goes to the dual. So we take the points, we take a random sample of the points like in the LP type algorithm. But now what we do, we dualize. So we dualize the half spaces and we dualize the points. And we go and we switch the roles of the half spaces and the points, because in the dual, in the polar, the half spaces will be points, and the points will be half spaces. So we have the same setting of embracing and avoiding by this lamp. So we do this recursively. And now there are two things that can happen. So it may be that the sample N and H, they have disjoint convex hulls. And now we do just the same as in the LP type algorithm. So we look at the hyperplane that is perpendicular to the closest pair. we take all the violating points and we add them to the sample and we recurse again. And this we repeat. And if this happens d plus 1 times, then we know after d plus 1 times, as in the LP type algorithm, that we found a closest pair. So assume, and we're done. So if this happens d plus 1 times, if we're in this case d plus 1 times, we're done. That's good. And but of course, it may also be that n and h intersect. And so that means we get a point of, so we get the closest pair in the dual. And now what do we do? So we get the closest pair in the dual, and so we get some point on the H polytope defined by the dual of n that gives us a closest pair, which we call Z. And now it may be that there are some points of some dual half spaces for P that violate Z, and we again add them to the sample, and we recurse again on the larger sample n. And we also repeat this. And again, as in the LP type, and we know if this case happens, so we can prove that if this happens, then this will just continue, right? So we will, so if this case occurs, we will just stay in this case. So it cannot happen again that if we, after we were in this case, that H and N intersected, and we add points to N, that that again we get separated points. And so that means in the dual we will remain separated. And again, after we know that every time we do this, we will get one more hyperplane that is in the basis, and or one more point of P that is in the basis in the primal, and then we just repeat, and we know after d plus 1 recursive calls, we get the true closest pair. And so this means we are just in the same setting as, or it's now very similar as in the LP type algorithm, that we know that we have to do at most a bounded number of recursive calls, but now it's not d plus 1 recursive calls, but 2 d plus 1 recursive calls, because it may be, so in the first recursive call we have nothing, then we somehow accumulate one basis for one side and then one basis for the other side. And so now let me very quickly try to analyze the running time. So basically the running time is we have d plus 1, 2 d plus 1 recursive calls, and then we switch the roles of the points and half spaces. So somehow if we go into the recursive call, the role of m and n switches. And also we can see using the theory of VC dimensional and epsilon nets that we need to have only a quite small sample, and also the violators that we add, they are also not too many. And so that means after one recursive call, we can reduce the number of constraints. But now the good thing is that because we switch the roles of the hyperplanes and the points, basically in both sides, we reduce the number of points and the number of half spaces. And so then basically now, if we solve this whole recurrence, we get something which is linear in the number of constraints and the number of points, and exponential in D as desired. Okay, and so I think this is all that I wanted to say about this. Maybe one more thing. So there also, I mean, I am missing one. So I didn't put it on the slides, but there also exists something, the so-called implicit LP type framework by Chan. So I mean, the way I described it, it may seem that maybe our algorithm is the only one that achieves this kind of running time, but this is not true. So there also exists this implicit LP type framework by Chan that also gets this running time in somehow off the shelf. But I would claim that our algorithm is slightly simpler and more intuitive, and his framework is very general, but it's a bit harder to use and uses some more heavy-duty tools, and maybe also gives some worse constants. But it's also there. Okay, so and with that, I think I would stop unless somebody wants to ask any questions. Thank you.
Thank you, Wolfgang. Any questions? I will actually ask one main question. Sure. So why do you so this can you explain this fact that you need at most d+1 round. So why do you get one constraint that will form a basis at every step?
So let's see.
Maybe I'm misunderstanding something, but somehow I don't. Yeah, I don't see it.
So if you
can you remind us the process again, please?
Okay, so maybe so this is already true for the LP type.
Yeah, even in that setting, what would be?
Yeah. So maybe it's intuitive from the picture. So so what? Let's see. So in this picture here, I want to. So basically here I have the convex hull of the points to the left, and I have this intersection of the half spaces to the right. Right. And what I do is I take a random sample, and I take and I compute the point that is. And I compute the phase of the random sample here of this blue polytope that is closest to the red polytope, right? And then I look at all the points from the point set that were not on the sample and that lie to the right that are closer to the blue to the red polytope than this phase, right?
Yeah.
And now my claim is that at least and so I'm looking for the facet of the whole polytope that minimizes the distance. And I say that at least one of these points that violate this half space, one of these points has to be on this facet.
So it's not that you're taking a random sample of those; you take all of those, and then
take all of them. Yes, I take all of them. So I'm saying I take all of them, and basically, assume. I mean, if all of the points of the basis were to the left, right, then the basis of the whole thing wouldn't be closer than.
Yeah. This I understand. Yeah, this I understand.
And yes, so I take all of them. I don't take a random sample. I take all of them, and then I use this epsilon net theory to show that this will not be too many, right? So I mean, basically, you have to balance the size of the sample. So you have to make the sample large enough so that you don't add too many points in each step.
Okay.
Right?
Okay.
But it has to be small enough so that the recurrence works out.
Okay.
The magic of that I did not quite explain. Yeah.
Great. Any other questions? Okay. If not, then thank you, Wolfgang.